Well, hello guys, I'm back with another new video. So I hope all of you are doing well and staying at home, maintaining the lockdown rules. So in this video we are going to plot some interesting graphs and how to plot the basic algebraic graphs, some trigonometric function, some logarithmic function, exponential function, and mixing of all those functions. And most importantly, we are going to find what are the asymptotes corresponding to a curve. So what is called an asymptote, how to find an asymptote corresponding to a curve, that I will also briefly discuss in this video. So I think all of you will enjoy this video, and we are going to have fun plotting all those graphs. So without wasting much time, let's start to get into the video. Be helpful to a large number of students who are going for interview for PhD or M.Tech or any other job interview. So plotting graphs is an essential thing we should know about this. So like for especially PhD interview candidates, some institute also would like to ask you if you know the asymptotes, how to find the asymptotes of a given curve. So in this video I will also be teaching you how to find the asymptotes of a given curve, as well as I will discuss some basic algebraic function, some logarithmic function, some exponential function, some sinusoidal function, and some modulus, and some function which we can plot from the mirror image of some different function. So those all kind of graphs I will be plotting here, and I think this video will be really interesting. So please watch till the end of this video. So without wasting any time, just get into the video. So asymptote is nothing but a straight line. So a straight line will be called asymptotes of a given function if only if points, if we have a point P on the curve y equal to fx, and we draw perpendicular from P on a certain straight line. Say this is a straight line. So if this perpendicular distance goes on decreasing when x tends to infinite, y tends to infinite, or both. So like here, as x tends to infinite and y tends to infinite, this perpendicular distance from the curve and the straight line goes on decreasing. So we can say this distance delta will goes to 0 when x tends to infinite, y tends to infinite, or both. So we will then call this straight line asymptote of this curve y equal to fx. So asymptotes must be a straight line for a given function, and there are theories I will also show that every asymptote will be a straight line for a given curve. Okay, like here is a curve y equal to fx. As you can see, this straight line shown in the black color, we can call this straight line also asymptote of this curve y equal to fx. As you can see, the perpendicular drawn from this curve on the straight line, this is going on decreasing as you go to infinite. So for x tends to infinite and y tends to infinite, as you can see, this perpendicular distance from the straight line to the curve delta will tends to 0. So these conditions are satisfying. We can say that this straight line is asymptote of this curve y equal to fx. A straight line or the asymptote which should be a straight line corresponding to a function. Let's say we have a function which is varying like this with respect to x. So here y equal to fx is a function. Let us put a point p xy on the curve. Now certainly the tangent drawn to this point will be like this. So as you know from the theory of mathematics, we can find the tangent of this curve like this way. So mathematically you can write y equal y minus y dy by dx is equal to x minus x. So this is the definition of a gradient of a curve. So from this, as you can see, we can simplify like x into dy by dx. Put this y in the right hand side, then it will be y minus x into dy by dx. Now if asymptotes exist, then for x tends to infinite, this dy by dx and this part y minus x into dy by dx will be finite. So let's call that a finite number. This is m and this is a c. So if you can put, so how can you say that this dy by dx will be finite? So as you can see, if x goes to infinite and y goes to infinite, the slope of the curve going flatter and flatter. So flat means dy by dx will be constant. So if you put in this equation, so you will find y equal to mx plus, for this part it is c. So under the condition of asymptotes, you find that the tangent, which is a straight line down to the curve. So this tangent we can say is the asymptote of this function y equal to fx. Given function y equal to 1 by x minus 5. So you need to first realize how this function varies with x. So this is a basic function. If you plot this function, you will find that the function varies like this. So this is a odd function and this is a symmetrical about the opposite coordinates you can say. So this is x equal to 5. Now as you can see, here exists two asymptotes. One is parallel to x axis and another is parallel to y axis. So parallel to x axis, the ax axis itself is asymptotes. As you can see, as x tends to infinite, this perpendicular distance tends to 0 as at x tends to infinite. So you can say one asymptote is y equal to 0, which is parallel to x axis. So this is parallel to x axis. So the self coordinate axis is the asymptote here. And the another asymptote, as you can see, this ax equal to 5, this straight line will also be asymptote corresponding to this curve. How? So as you can see, this x equal to 5 for y tends to infinite or y tends to minus infinite, you can see the perpendicular drawn to this straight line will goes on decreasing as you go to infinite. So this perpendicular distance will also be tends to 0 for y tends to plus minus infinite. So here two asymptotes are there. One is parallel to x axis, or you can say y equal to 0, and another parallel to y axis, which is x equal to 5. Now let us find the asymptotes for a function y equal to tan x. So first you need to know how to plot the curve for tan x. So how to plot this? So let's define the point as say pi by 2, pi, 3 pi by 2, and here also minus pi by 2, pi, and minus 3 pi by 2. So as you can see, tan x means obviously sin x by cos x. So for x equal to pi by 2, that is a 90 degree, tan x will diverge as cos pi by 2 is 0. So the function will be like this. So let me plot this dotted line here, it will be much more easier. So for tan x equal to pi by 2, the graph would be like this. Okay. So as you can see, at x equal to pi by 2, this tan x goes on diverging, and for the minus pi by 2 also. So you can say this one is an asymptote. Okay. So now what happens for the pi by 2 to 3 pi by 2 to region? So here also the curve is like this. So here you can see for ax equal to 3 pi by 2, this is an asymptote, as the perpendicular distance will also goes on decreasing at x equal to 3 pi by 2. So y equal to plus minus infinite condition are satisfying for these particular points. So these are all the asymptotes corresponding to this graph. So similarly you can also plot the function here like this. So as you can see, this is an asymptote, this line is an asymptote, this line is an asymptote. So for this particular function, when x equal to plus minus 2n plus 1 pi by 2, where n is odd, n is any integer 1, 2, 3, 4, then you can see all these asymptotes are here. So now let us plot from a simple algebraic function. So one function is like, as you know, well-known function y equal to x square and y equal to x to the power 4, or any even function. So in general we are going to plot x to the power 2n. So n varies from 1, 2, 3. Okay. So for this kind of function, as you know, these are all even function. So the graph will be symmetrical about the y-axis. So now for x equal to y equal to x square, so the graph will be like this. Let's say this point is plus 1 and this point is minus 1. Now if you want to plot y equal to x to the power 4 on the same graph, now this will be like this. So as you can see, for x less than plus 1 or x less than minus 1, this y equal to x to the power 4 varies more slowly than y equal to x square. And for x greater than plus minus 1, this y equal to x to the power 4 function will be much faster than y equal to x square. So as simple as that. So for any kind of x to the power 2n function, even function, you can plot this way. Only you have to remember this plus 1 and minus 1 point. So in that region you must be careful. Okay, so let us plot some other function, some odd function, let's say. So x y equal to x, y equal to x is easy, as you know, y equal to x cube, y equal to x to the power 5. So any function 2n plus 1. So any function which is odd power of x, how to plot all those graph? Y equal to x is a straight line, no need to plot all those things. So I am plotting y equal to x cube and y equal to x to the power 5. So now if you plot, so all these function are odd function. So this odd function will be symmetrical about the origin on opposite coordinates. So how the function will be like this? So the function will be like this. So if this is the function for y equal to x cube, now if you want to plot y equal to x to the power 5 on the same graph, then again you need to be careful about the plus 1 and minus 1 point, because this is the crucial region where the graphs varies differently for different power of x. So for y equal to x to the power 5, the graph will be more slow for x less than plus 1, and similarly for x less than minus 1, x to the power 5 graph will be slow, and for greater than plus 1 or greater than minus 1, the function will be faster. So the graph will be like this. So as you can see, this will be some more curve. I have stated like a straight line. So as you can see, so you can plot x to the power 7, x to the power 9, all this on the same graph. All you need to know, plus and minus 1, those region you need to be careful. Now let us plot some inverse function like y x to the power 2n plus 1 and y x to the power 2n. So the first one, which is an odd function, so this will be symmetrical about the origin on the opposite coordinates. So if you want to plot for n equal to 0, then y is obviously 1 by x, n equal to 1, 1 by x cube, and similarly 1 by x to the power 5. Now if you plot y equal to 1 by x, which is a reciprocal function, so the graph will be like this. So in this region and on this region. Now if you want to plot the same, if you want to plot the 1 by x cube function on the same graph, then again you need to be careful about the plus 1 and minus 1 region. So now, as in the previous case, x less than minus 1 and x less than plus 1, x cube was varying slower, but as this is reciprocal, here x cube will be much faster. So here as you can see, x cube will be much faster for x less than 1, and for x greater than -1, that is this region, here also as you can see 1 by x cube will be much faster. So this blue line is your 1 by x and this black line is your 1 by x cube function. Similarly, you can plot 1 by x to the power 5 on the same graph, keeping those mind the limit x greater than -1 and x less than +1 limit. By x to the power 2n, as you know, this is an even function, then the graph will be symmetrical about the y-axis. Let us plot y equal to 1 by x square. So the graph will be like this. This is x, this is your y. So 1 by x square will be like this and this. Again denote +1 and -1 point. Now if you want to plot y equal to 1 by x to the power 4 on the same graph, then again you need to careful about the +1 and -1 limit. So x to the power 1 by 4 will be varies like this, and here like this. So as you can see, this is y equal to 1 by x to the power 4 and this one is 1 by x square. So for x less than +1, 1 by x to the power 4 is varying much faster. So the amplitude will be much more high. Okay. Similarly, for x greater than -1 region, that is this region which is x greater than -1, here as you can see 1 by x to the power 4 has higher magnitude or varying much faster than the 1 by x square graph. So you can plot all those x to the power 2n function, this even function like this ways, keeping in mind those +1 and -1 region. Now let us plot some irrational function like y equal to √x, y equal to 1 by x cube, y equal to 1 by x to the power 5, all those irrational function. So before plotting all this, you need to remember one thing. If fx is x to the power n and gx is 1 by x to the power n, then gx will be, so here gx will be mirror image about y equal to x for the function fx equal to x to the power n. So if you know the function fx equal to x to the power n how to plot, then you can easily plot gx equal to 1 by x to the power n. So it will be mirror image of fx about y equal to x axis. So for example, so let's plot y equal to x cube and y equal to 1 by x cube. So as you can see, this is your gx and this is your fx. So this gx will be mirror image of y equal to x cube. So how to visualize that? So let's plot first y equal to x line. So this is your exactly y equal to x line. So this is your y equal to x. Now how do you plot y equal to x cube? So as I discussed earlier, y equal to x cube is like this. Okay. Then I have said that y equal to 1 by x cube will be mirror image of y equal to x cube. Let's say you have a mirror on this y equal to x axis, then your y equal to 1 by x cube curve will be varying like this. Or let us use another color. So I am plotting using the black color here. So this is your y equal to x cube and this black line is y equal to 1 by x cube. So similarly you can plot y equal to x to the power 5 and y equal to 1 by x to the power 5 in this way. So this mirror image concept is very much useful for plotting some graphs of a known function. Y equal to x square, which is your fx here, and y equal to x to the power 1 by 2, that is root over x. How to plot that function? As you know, but for this function you need to be careful that we cannot take y as imaginary. Okay, so for y equal to x square, the graph is like this. Okay, let's say this is your +1 point. Then y equal to root over x, so this is your y equal to x line. Now for y equal to root over of x, then the graph will be like this. So this is exactly the mirror image of y equal to x square. This is y equal to root over of x. Now if you want to plot y equal to x to the power 4 and y equal to x to the power 1 by 4, say on this same plot, then how will you plot? As you know, y equal to x square will be varying slowly in the x less than 1 region. So this is your y equal to x to the power 4. Then your y equal to 1 by x to the power 4. So this will be like this. So for 1 by x to the power 4, this will be varying faster than the 1 by x to the power 1 by 2 graph. So I have plotted it here. So this is your y equal to 1 by x to the power 1 by 4. So as you can see, this mirror image concept is very much useful for plotting some kind of function. Now let's say if you have a function like this kind, say 2x square minus x to the power 4, how do you plot? As you know, so you have learned how to plot y equal to x square. So this is x and y axis. So you know y equal to x square graph varies like this way. Okay, so this is x square graph, or you can say here 2x square, and y equal to x to the power 4, but here is y equal to minus x to the power 4. So the graph will be in the negative region. So y always will be negative. Now for this given function y equal to 2x square minus x to the power 4, the resultant of this curve will be like this. So it will be varying like this. So as you can see, here will be two maximum, one is at +1 and another is at -1. So as you can see, this x to the power 4 is much more powerful. So this resultant curve will be bent in the y equal to x to the power 4 region. That is why I have plotted like this. Minus 2x square plus x to the power 4. So I have just alternated the sign than the previous case. Now similarly in this case, if you plot y equal to minus 2x square, then certainly this will be negative. So this is y equal to minus 2x square. Now y equal to plus x to the power 4, the graph will be like this. Now the resultant of this graph will be like this. So this is not symmetrical, this should be symmetrical. So this is your +1 point, this is your -1 point. So for this case you have find two minima, one at +1 and one at -1. You can easily find the maximum and minimum of this point by putting dy by dx equal to 0. So here as you can see, here x to the power 4 and here x to the power minus 2x square. So again, as x to the power 4 is much more powerful, the whole graph bends towards the positive region. So for y in the positive region, that whole curve belongs to that. Also, as you can mention how to know the maximum or minimum point of this function, so you can plot this graph by finding also maximum and minimum point. Then you can also realize that for this case, this +1 and -1 is the minimum point, but in the previous case that +1 -1 was the maximum point. Sinusoidal function and mixing of algebraic and sinusoidal function. So let us plot some sin x. Sin x is easy function, as you can see it will vary sinusoidally. So for x equal to 0, sin x is 0, pi by 2, this will +1. So this will vary between +1 and -1 amplitude. So it is a easy graph, no need to discuss these things. But the tricky part of how to plot sine of x square. So sine of x square you can write as, so this was the graph asked in the RRI interview. So you can write x square as x into x. So as you can see, this frequency part is x dependent. So you can compare this graph with x equal to omega into t. So your t is x here, omega in x. But the interesting part is, as in the, you can say in the simple harmonic case, motion omega is constant, but here omega is varying. So sin x graph will be same as like this. Only the thing is that the frequency will be goes on increasing. So how will be the graph look like? So the graph will be look like this. So amplitude will be same, but this frequency will be much more higher. So this is the graph for sine equal to x square. Okay. So at the first glance you will be surprised with this function, but it is a easy function. Only you need to vary the frequency. So this waves will be much more close as you increase the x. Okay. Y equal to 1 by x into sine x. So this amplitude part will be varying as 1 by x. Keeping in mind that you know that 1 by x graph varies like this, right? So the amplitude of the sine x function will also goes on decreasing as x will increase, right? So how to plot? Obviously it is a even function, because if you put x to minus x, you will find that y equal to y of x. Okay, obviously this is a even function, so it will be symmetrical about the y axis. So the graph will be like this. So as you increase x, this amplitude will decay as 1 by x. So as you can see, this amplitude is decaying as 1 by x. So here as you can see. Okay. So this is a pretty much easy. Similarly, you can plot also cos x, cos of x square, 1 by x into cos x. I am not plotting all those things, just like similar in the case of sin x. So plot y equal to cosec x. So as you know, fx equal to 1 by cosec x, which is nothing but 1 by sine of x. So this is a function for a typical sin x function. Now you need to know, so at ax equal to pi by 2, sin pi by 2 is 1, but cosec pi by 2 will be just 1. So 1 by 1 will also be 1. So the graph will be like this in this region. For x greater than 0, less than pi, this region cosec x will be varying like this. Okay, so as you can see, when x equal to 0, then sin x is 0, then cosec 0 will be infinite because it is 1 by 0. Okay, so that is why at x equal to 0, here cosec x is infinite. Similarly, for sin equal to plus pi, sin pi is 0, again satisfies the similar condition, 1 by 0 is infinite. So this graph is going to the infinite. Okay, now again similarly in this region you can also plot. So this is a continuous function, it will go like this, sin x. So again cos x will be like here, and for the similar case, for a negative region, cosec x will be like this. So similarly you can plot also for x negative values. So in this region, as sin minus pi is 0, then cosec x will diverge, and again sin minus 2 pi is 0, then cosec x will also diverge. So similarly for the negative region, for x equal to minus pi by 2, in this region cos x will be like this. So here cosec x is a discontinuous function, depend on the sin x value, so it will sometimes go on diverging, and also it will also be starting from the plus 1 value or minus 1 value. So similarly you can also plot for fx equal to sec of x, as it is 1 by cos of x. So if you know how to plot cos x, then you can easily plot fx equal to sec of x, just similarly in the case of fx equal to cosec x. So that's it for the first part of this video in this graph session. So I had lot of fun plotting all these graphs. I also like to know what are your opinion about this video. So in the second part of this video, I will be plotting some sine inverse x, cos inverse x, some logarithmic function, some exponential function, and also some modulus function depending on the mirror image concept. So that will be much more helpful. So stay tuned for that for coming part 2 videos. So thank you for watching this video till the end. I hope all you have enjoyed the video. So if you like this video or this kind of video in future, please like my channel and subscribe, and share this video as many as possible, so that much more people get benefited from this video. So thank you, bye bye, stay tuned for the upcoming video.